Okay, welcome to Chapter 7 of the PowerPoints by Wade. Here we're going to get into the structure and synthesis of alkenes. Remember last time we finished up with elimination chemistry, so we learned how to form pi bonds and so to make a double bond. Here we're going to get into the chemistry of double bonds. So before doing so, let's talk about the structure and what alkenes are. Alkenes are hydrocarbons with carbon-carbon double bonds. Note the ending ENE as opposed to ANE for alkanes. So alkenes will be a special ending to keep in mind. Alkenes are also called olefins, which means oil-forming gas. Okay, the functional group of alkenes is the carbon-carbon double bond, and this is the group that gives alkenes their reactivity. So alkenes will have a special reactivity that alkanes did not. Here if we look at ethylene, which is a carbon-carbon double bond with two hydrogens on each carbon, note that we have a single bond formed by two sp2s overlapping, and so here this is a sigma bond, and then we have the two p orbitals that are overlapping. Even though it shows that they aren't, okay, these are really very close to each other, and so they do overlap, and we'll often designate that overlap by drawing two lines between the p orbitals. And so you have half of a pi bond up here, and we have half of a pi bond down here. That's how we'll want to view a pi bond. Okay, so the sigma bond, again, which was the internal part of the double bond, okay, is around the double bonded carbon made up of sp2s overlapping. The bond angles are 120 and the geometry is trigonal planar. Okay, so this is kind of a review back when we were discussing hybridization theory. And as we just discussed, the unhybridized p orbitals overlap with one another to form the pi bond. Okay, so the double bond is not a pi bond. The double bond is made up of a sigma bond and a pi bond. Okay, so here's a description of the bond lengths and angles. Okay, you can see it's approximately 120 here. Okay, the bond length 1.33 angstroms, somewhat shorter than the single bond. Okay, so we know as the bond order increases, going from a single to a double, the length decreases. The atoms are being squeezed together, and if you continued on to make a triple bond, it would be an even shorter distance. The other thing to note is that sp2 hybrid orbitals have more s character than sp3s. Okay, so the way you figure that out, I have one s and two p's, so 1/3 of the sp2 is s character. Okay, so I have 1, and the total is 2 plus 1 for 3. Down here, I have what? 1/4 s character, don't I? Because I have 1 divided by 4, which is these 3 plus the 1s. And so sp2 has more s character because 1/3 is greater than 1/4. Okay, so again it's showing why there's a shortening of the distance between the two carbons. It's because the pi overlaps squeeze the two carbons closer together. Here we see the pi bonding in a little bit more detail. You can show it like this with the two p's overlapping. Here, bringing in the orbitals to show the smearing effect between the two p's. Here with the space filling model to show kind of an electron cloud above the carbons on top and bottom. Okay, and because we have this pi bond, this introduces us to the possibility of new kinds of isomers, the cis-trans. Remember, we covered that with the cyclics, but you can now have it if you have a double bond. Here the two CH3s are on the same side, so this is what's called the cis isomer. And over here the CH3s are on opposite sides of this double bond, and so you have the trans isomer. Okay, the point here is that we cannot interconvert the cis and the trans, because if I tried to twist, I would end up breaking the pi bond. See that? And if you break the pi bond, you break the molecule. So cis and trans isomers are two distinct molecules. Okay, so here we talk about what's called the element of unsaturation, or sometimes called the degree of unsaturation. Okay, so when we talk about saturation, we're talking about the hydrogen atoms in the molecule. If you look at an alkane, any alkane is fully saturated. It has the maximum number of hydrogens as possible. When I introduce a double bond, note that I have to take away a hydrogen here and a hydrogen here. So I end up losing two hydrogens, and when I lose two hydrogens to form this double bond, I gain what's called a degree or element of unsaturation. I can do the same thing if I form a ring. If I form a ring, look, I end up losing two hydrogens from the saturated case. The saturated case has 8. The unsaturated has 6. So again, I lost 2 hydrogens. Okay. I can gain an extra degree of unsaturation by putting a triple bond here. Note I now have 4, so I lost 2 more, so this would have 2 degrees of unsaturation. Okay, but back here, note that I can gain a degree of unsaturation either by having a double bond or a ring. And so that's the first point to realize, is that if I have 1 degree of unsaturation, that tells me automatically, write it down, that the molecule either has a double bond or a ring associated with it. So here we see this all summarized. Okay, don't have to worry about this thing here. So how do we calculate degree of unsaturation? Okay, very simple. You first find the number of hydrogens the carbons would have if the compound was fully saturated, then subtract the actual number of hydrogens and divide by 2. This calculation cannot distinguish between multiple bonds and rings, but it does tell you that you either have a double bond or a triple bond or a ring in the molecule. So here is an example. Suppose we had a molecular formula of C5H8. Okay, the first thing I need to do is to calculate the saturated case. So the saturated case would be what? C5H what? 2n plus 2. Remember that? So 2n would be 2 times 5 is 10 plus 2 to give us 12. So that would be the fully saturated case. Now what we do is we take our 12 in our saturated case and we subtract from the 8 from it and divide by 2. So we get 4 over 2, or this compound has 2 degrees of unsaturation. And so what are the options? The options is it could have 2 double bonds, it could have 2 rings, or it could have a double bond and a ring, or what's the other case? They didn't have it here. You could also have a triple bond as a possibility. Okay, we don't know, but it's going to be one of those options. So here, what do we do if we have heteroatoms, that is, other atoms besides carbon and hydrogen in the molecule? Okay, the first thing to look at are the halogens. Halogens replace hydrogen atoms, so when we calculate the degree of unsaturation, we count halides as hydrogen atoms. So they make that correlation. Oxygen does not change the ratio. So oxygen count does nothing to that. And nitrogen, since it's trivalent, okay, it will actually have an extra hydrogen. So we want to add the number of nitrogen atoms when calculating unsaturation. If you watch my lecture video, I make this much more easier to understand. This is a very complicated description of what's going on. So please watch the video that I have on YouTube to understand this. Okay, so they proceed through an example. Suppose you had C4H7Br. Okay, so here I want the saturated case. What is the saturated case? Well, this C4H7Br, okay, remember that the halogen acts like a hydrogen, so I'll end up adding it to that count. So this thing is acting as C4H10. What is the saturated case for C4? It's 2n plus 2. So 2n is 8 plus 2 is 10. Okay. So when I look at what I have C4H8 compared to C4H10. So I'll subtract the 2 and divide by 2, so this thing has 1 degree of unsaturation. Okay, so when I go here, okay, remember halogens add to the hydrogen count. Halogens like halitosis, bad breath, they add to your breath to give you bad breath. Suppose we had nitrogen now in the molecular formula. Nitrogen, N, stands for negative, so I have to subtract from the hydrogen count. So this thing is going to act like C6H6. Then what is the saturated case for C6? 2n plus 2. So 2 times 6 is 12, plus 2 is 14. Okay, so here we can take 14 minus 6, which gives us 8, and 8 divided by 2 gives us 4 degrees of unsaturation. They did not do this right here. This is just awful. Okay, let's go on to alkene nomenclature. Just a couple of extra rules from what we learned about alkanes. The first rule is we find the longest continuous chain that includes double bonds. Okay, so my parent chain now will include a double bond. Secondly, my ending changes from ANE to ENE. Thirdly, I want to number the parent chain so that the double bond has the lowest number possible. If I have a ring, the double bond is assumed to begin with carbon 1. Let's take a look at some examples. Okay. So here I have a 4-carbon alkene, so I'll want to number from this end because the double bond is closer to this end. So we get these numbers, and the number I put out in front is where the double bond begins. So I have 1 butene, and again this ending is telling me that I have this double bond. Same thing here. I have 1 pentene, a 5-carbon. Note I could have isomers. I could have 2 pentene if the double bond was here. Same thing over here. I could have had 2 butene, which is what we have down here. If I had a double bond in a ring like cyclohexene, okay, note I start numbering here and I number through the double bond. Okay, this is an important rule. I start with 1 and I got to proceed in this direction to go through the double bond and then continue. I don't have a number out in front because with a ring it's always assumed that the double bond will begin with 1. Okay, here's some other examples. Suppose we had a group on the ring. How would I number the ring here? I would do it like this, wouldn't I? Start the 1 and then number through the double bond to go that way. And so this would be 1-methyl cyclopentene. How about over here? Well, the double bond is here. I have to give priority. Okay, which of these two will be 1? It'll be this one, won't it? Because I have to number through the double bond. If I would have started here as 1, temptation to try to go up here and make that 2. No, I've got to, if I started this as 1, then this would have to be 2 because I have to number through the double bond. And so I'd get all the way back over here and make this 5 to get to the CH3. Okay, so this ends up being 3-methyl cyclopentene. What happens if I have more than 1 double bond in the ring? Well, now my ending changes to diene or triene or 4 of them, tetraene. And now I must number where these double bonds begin. So here they begin on carbon 1 and carbon 3. So I have 1,3-butadiene. Here, my first double bond is on this side, so it makes sense to number this 1. So I'd have a 1, a 3, and a 5 heptatriene. And then this cyclic one here. Okay, so note when I have a ring, I have to use numbers to tell you where those double bonds are in the ring. Okay? So we're going to stick with this old IUPAC system where I put the numbers in front of the name. What about cis and trans isomers? Okay. Here I have a 2-pentene, don't I? But now what I am seeing is I can have two kinds of 2-pentene, where I can have the hydrogens on the same side of the double bond or on opposite sides of the double bond. Okay, so what I do is I always draw a line through the double bond and ask which side are my hydrogens on. If they're on the same side, I have the cis isomer. If they are on opposite sides of the double bond, then I have the trans isomer. Okay, so I put cis and trans in front of the name. Over here, these are neither cis nor trans, because in order to get cis or trans, I've got to have two of the same atoms or groups on these two carbons here. And so here I have two hydrogens. Over here, I don't have two of the same on each carbon. So these are what are called geometric isomers. Okay. Cyclic compounds, again the 6-membered, cyclohexene, cyclooctene, and so on. Another way to name the type of double bond is using the EZ nomenclature. Okay? It's kind of similar to cis-trans, but let's see what the differences are. Okay, what we're going to do is prioritize the groups. Okay, if the prioritizations are on the same side, we get the Z isomer. If they are on opposite sides, we get the E isomer. Example. What we do is we look at each carbon of the double bond individually. Let's look at this one first. It has these two atoms on it. Which one has higher priority according to our stereochemistry rules? The bromine does, doesn't it, since it has the higher atomic number. Now I come to the other carbon. It has a CH3 and a hydrogen. This will have the higher priority. Now I draw my dividing line. They are on opposite sides. And so this will be what? The E isomer, won't it? Okay. Note, in order to use E and Z, all 4 groups on the double bond are different. Okay. When I use cis and trans, I had 2 of the groups being the same. Okay, so here's some cyclic stereoisomers. We won't deal much with these. Okay, stereochemistry with Dienes. Okay, so each double bond could be E or Z. Okay. Some commercial uses of ethylene. Okay, you can read the book on this. Propylene, polymers. Okay, we won't deal much with polymers, but double bonds have the ability to polymerize and so produce many repeat units. Okay, and get polymers, which are very high molecular weight molecules. Okay, you can imagine attaching a bunch of paper clips together. Okay. And so we get these different polymers like polypropylene, polyvinyl chloride, polytetrafluoroethylene, and others. Okay, but you can read the book or take an additional course regarding polymers. Heats of hydrogenation. Okay, this is another way to tell you how stable double bonds are. Okay, and we covered this using Zatev's rule. Okay, but we won't get into this much here. Okay, it's again showing you that as I get a more highly substituted double bond, it's more stable than a lesser substituted double bond. The other thing to see here too is that the trans double bond is more stable than the cis double bond. Okay, and again looking at substituent effects. Okay, just a review. Cyclic alkenes, looking at their heats of hydrogenation. We won't spend much time on this. Okay, just continue through this stuff here. This isn't that important. Bredt's rule. Okay, let's look at this for a little bit. A bridged bicyclic compound cannot have a double bond at a bridgehead carbon unless one of the rings contains at least 8 carbon atoms. Okay, so the bridgehead carbons are here and here where this bridge is. Okay, and so what Bredt's rule is saying is that I can never have a double bond at a bridgehead carbon. That would be an illegal structure. Okay, some physical properties of alkenes. They tend to have low boiling points with increasing mass. Branched alkenes have lower boiling points, just like branched alkanes. They tend to be less dense than water and tend to be slightly polar due to the pi bond. Cis-alkenes have a greater dipole moment than trans. Okay, and so the cis will be slightly polar compared to the trans, which is nonpolar. And so that helps make the cis-alkenes have a higher boiling point than the trans alkenes. So we see this kind of thing summarized here. See how the trans dipoles cancel, but the cis dipoles add up in the same direction to give you a small dipole moment, which helps to increase its boiling point over the trans. Okay, just a review of how to make alkenes through E1 and E2 chemistry. Okay, so remember the mechanism of the E2. Base attacks a beta hydrogen, forms the pi bond, kicks off the leaving group. So we have a strong base attacking a beta hydrogen. Okay, bulky bases that could try to attack beta hydrogens include the T-butoxide ion and these others. Okay, and if you have watched the video we did some examples of this one here, where this bulky base can attack the less substituted beta hydrogen. Okay, and so the non-Zaitsev product will dominate. Okay, so make sure you watch that video for this understanding. Okay, sometimes we can get what's called the Hofmann product. Okay, where the Hofmann product is another way of stating the non-Zaitsev product. And that's again if we're using a bulky base. Note here they are not using a bulky base, and so the Zaitsev product is the major product. Okay, you can look into E2 reactions. They can be stereospecific. Okay, again showing the coparaplanar geometry here. So the base attacks the beta hydrogen anti to the bromide leaving group. Okay. Here are E2 reactions on cyclohexanes. Okay. The key thing here on cyclohexanes is that my beta hydrogen must be axial and my halogen leaving group must be axial, so it follows this coparaplanar geometry. And so after this attack I can get a double bond forming right here. If this hydrogen here was not axial, then I would have to do a ring flip to get it axial. Okay, so again, watch the video as I cover this stuff in a lot better detail than these slides can present. Okay, let's just skip over this stuff here. The E1 mechanism, again, all review from the last chapter. You can get a dehydration of alcohols to form a double bond. We typically use sulfuric acid or phosphoric acid and heat. Okay, so anytime I use one of these two acids in heat with an alcohol, it'll form a double bond between the two. Okay, so here's an example of the mechanism. The alcohol oxygen gets protonated, so we form water as a leaving group. The water then leaves, forming this carbocation. Then the weak base water attacks the beta hydrogen, forming the pi bond to give us a double bond here. Okay, just move right through this stuff here. Not important. And that's it.